Okay, hello everyone. So I am going to do another round of Q&A for kids and others. And our topic again today, same as last week, is science fiction, what could be real? So we have a few questions that were left over um, from last week, and maybe I could start with these. So the first one listed here was, how long before we colonize Mars? Interesting question. I think what has driven colonization in the past on the Earth is, well, it's partly just people seeking out new places to live and so on, but it's also partly the idea that there would be some valuable goods that could be got from the mysterious place over the ocean that you could then sell in the place you came from. And I'm not sure how that's going to work out with the moon and Mars and so on. I mean, what are we going to use them for? I think I certainly know people who think that we should be a multi-planet civilization, and they talk about things like, well, why don't we have a backup on another planet? And I have to say that things like the pandemic that we're in right now don't incredibly encourage that idea, because it kind of only takes, one trip from the spacecraft to deliver the virus to the colony on Mars. It's not quite as separated. Just because you're on a different planet doesn't make you quite as separated as you might have thought. Um, but first question is, why go to the effort to do this? Then the next question is, how hard is it going to be to do it? So I think one of the questions is, like, what are we going to do on the moon, on Mars, and so on? And it's always an interesting problem when you think about new technology, new possibilities. I remember when I was a kid, there were all these books that talked about, in the future, we will have cities under the oceans. Well, turns out we don't. Why not? Well, because it's not that useful to do that. So far as we can see, there isn't an immediate use case that that people have come up with. Why don't we have? We could have sort of a lot of people in Antarctica. We don't have very many. We have a few doing things like doing astrophysics experiments that are much more conveniently done at the South Pole than elsewhere, or particle physics experiments. People studying things that are best studied in Antarctica, but it's not like we have a bustling metropolis in Antarctica. So, what could be done on the moon, for example? So, for instance, on the far side of the moon, because the moon always has one side pointed towards the Earth and the other side away from the Earth, the far side of the moon is, for example, a very quiet place when it comes to radio signals. So, for example, if you wanted to build a giant radio telescope that would let you survey the universe in the radio spectrum, if you do it near Earth, well, there's all kinds of radio emissions from the Earth, radio stations, cell phones, all this kind of thing, all kinds of satellites orbiting the Earth that have radio communications. The far side of the moon, there's none of that stuff. It's always turned away from the Earth. And until somebody decides to start putting communication satellites around the moon, there's just no human-created radio emissions there. So that's an example of something one could do. Now, when it comes to Mars, it's much less clear to me what we will. In terms of the moon, let me give you some examples. So people said, well, let's mine stuff from the moon. They said, let's mine. What can we mine from the moon? There are asteroids, for example, that are rich in certain metals that are not so common on Earth. The moon, it's pretty similar to the Earth. It's probably because it was formed sort of more or less, most of it was formed more or less at the same time as the Earth. There were a few ideas. Like, I had a friend who was first of all thinking about mining helium-3 on the moon. I couldn't quite figure out why. Then he had the idea, let's mine moon rock. And we have diamonds on the Earth, which people turn into gemstones, and they're very valuable, and so on. It's like, gosh, if you could give somebody a piece of moon rock, wouldn't that be a more valuable thing than giving them a diamond? I encouraged him to figure out, because diamonds, in addition to being rare, somewhat rare, the big ones are rare, they also have the feature that they refract light in a really cool way. So when you have a diamond, light goes into the diamond and it bounces around inside the diamond and then eventually comes out. And it's that bouncing around inside that makes diamonds sparkle. Well, there's no reason to think that moon rock would do that same kind of thing. And actually, a big issue with diamonds is to know exactly how to cut them, exactly what shape to make, so that you maximize all of those bouncings around inside the diamond crystal. So it's like, can you do that for a moon rock? Don't know. But that's a pretty thin reason to go to the moon. I mean, there are other things like send a spacecraft to the moon and you know, have send back a video, and that'll be valuable. So it's like, you know, go to other planets for entertainment. That's again a little bit of a thin reason. So okay, so that's the why go there, and it's not completely clear. And also on Mars, there's another issue, which is, you know, maybe possibly there was life similar to terrestrial life on the Earth that existed on Mars at one time. Who knows? Maybe it evolved separately. More likely, it was probably seeded by some common source. Who knows? There are meteorites that managed to get from Mars to the Earth, and probably vice versa. So things could have gotten spread that way. But in any case, if we go colonize Mars, then it's like, you know, we will certainly, like, for example, one person I know had this idea, let's turn Mars into something more like an Earth atmosphere by taking the water that is in ice form at its poles, and let's put it in the atmosphere. And you can do that by blowing up a bunch of hydrogen bombs on the poles of Mars. Maybe you can do that. It's not clear you can. But you know, it's like, well, if you do that, then if there ever was little microfossils of life on Mars, you just completely destroyed them. So in any case, that's the issue of you know, what's the you know, not to say that it isn't a really cool thing to go to Mars and so on, but the idea that there's an immediate, you know, there's an immediately useful thing to do is not so clear to me. Now there's the question of how do you get there? Well, one of the main problems is it depends on exactly where Mars and the Earth are in their orbits and so on, but it's going to take a while, maybe 6 months to get there. And one of the things that will happen is that when you're still near the Earth, you're sort of protected by the outer, the magnetosphere around the Earth and things like this from some of the radiation that comes from the sun. If you're in space, deep space, you have things like solar flare. It's when the sun produces sort of a big flare on its surface that splurts kind of radiation out into space. And it's not clear how you shield from that. That's one. I mean, you can, but it's not. That's a challenge. And then there are also challenges like, how do you really, you know, how do you succeed in a spacecraft in keeping sort of the environment stable and having and so on. When you get to Mars, you know, you don't. It's not so easy to start just you know, growing crops on Mars or something like this. It's not so easy to get a self-sustaining ecosystem on Mars. And experiments that have been done on the Earth to try and make self-sustaining ecosystems have not been terribly successful. So that's another challenge. So I think there are a bunch of challenges, and you know, it's kind of a sad thing, because when I was a kid, like let's say 50 years ago, I was really interested in space. That was the time when the moon landings were happening and so on. And everybody, including me, just sort of assumed there'd be spacecraft going to Mars and there'd be Mars colonization. In fact, I even produced little sort of notes, which I still have, about, you know, what would happen in the 1980s, what would happen in the 1990s. And it was like, for me, back in the 1960s, it was like, of course we'll colonize Mars by the 1990s or the early 2000s. And it's sort of disappointing that hasn't happened. But it is also technically challenging, and one has to sort of have sort of there's a question of why do that, so to speak. Let's see. Well, there are all kinds of questions here. Another question here is, why isn't a tricorder available yet? So a tricorder is this thing in Star Trek. Tricorders do all kinds of things, but mostly they sense stuff about things remotely. So you point a tricorder at a rock, and it tells you what kind of rock it is. You point a tricorder at a person, and it tells you what's wrong with them, those kinds of things. So it's like being able to just look at something and tell things about it. Actually, we're getting closer to being able to do things like that. So what happens when you look at something with your eyes or whatever, you can see some things about it. You can see what color it is, you can see what texture it has, what shape it has, all those kinds of things. But if somebody shows you a rock, maybe if you're a good geologist, you can say, well, I recognize that kind of rock. It's a such and such a kind of sandstone, whatever it is. But if somebody says, well, how much aluminum is in that sandstone? You're like, oh, I don't really know. You know, it's typically this or that, but you can't really tell. And so the question is, can you make a device that will immediately tell, you're looking at a piece of sandstone, how much aluminum is in the sandstone? Well, it turns out there are ways to do that. So we see with our eyes visible light, but there's also infrared, ultraviolet light. There's a whole range of different frequencies of electromagnetic radiation. And there are things that we can tell from looking at things outside of the normal visual range that will give us more information about them. In addition, if we shine a laser, for example, on the thing, and we look at what kinds of light come back from the laser hitting the thing, we can tell a lot about what the thing is. And the reason that happens is when laser light, any kind of light, but laser light is really good because it's very organized light. It's light of a very specific frequency that's coherent. And when laser light hits something, it all the little molecules in the thing, they absorb the laser light, and the molecules, when they re-emit the light, normally when you're looking at your hand or something, what's happening is light from whatever, your lamp or something, is hitting your hand, and then that light is being re-emitted from your hand, and that's the light that comes to your eye, and that's what you see. So the way that re-emission works can depend a lot on the precise molecules that are there. And when you use for example, laser light, and you look at exactly what gets re-emitted, do you get light of exactly the same frequency, or is it slightly shifted in frequency, and so on? When you look at that in detail, you can tell a huge amount about what the molecules in the material actually are. There's a thing that's called Raman spectroscopy, is one of the techniques that's used to do that. And so you could imagine something like a tricorder that uses kind of hyperspectral imaging. Hyperspectral imaging means you're going beyond the usual spectrum of light that we see to see other kinds of light. And in addition, you're sensing much more than just red, green, blue. You're sensing more than just the colors that we perceive. You're sensing precisely the frequency of light that's coming back. So if you do those things, it is possible to sense more stuff about a thing than what you can just see with your eyes. And actually, there are some devices that have come out in the last few years that allow you to do that. So for example, there's one device I have one of that's kind of cool, that you point at it like a piece of chocolate, and it will tell you the amount of fat in the chocolate. And it does that by using this this kind of detailed spectroscopy idea. So tricorders for telling what the detailed what a thing is made of, that's something that absolutely is coming. Hyperspectral imaging is actually already used with food to tell whether the food is bad or not. It's something that you may not be able to see visually, but you can see by looking at these detailed features of the light that is sent back from the food. It's also the case that one really cool thing that one could potentially do with these kinds of techniques is look. So normally, when so if you have like a fitness watch or something that's measuring your heart rate, the way it does that is using a thing called a PPG sensor. You'll see it typically flashes green light. If you take your fitness watch off, it'll have flashes of green light. Those flashes of green light are basically they're going through your skin, and they are the watch is trying to see exactly what light is sent back from the blood that's underneath your skin. And depending on whether that blood has, depending on whether there's more oxygen or less oxygen in the blood, the exact color that's sent back will change. And so when your heart beats, every time your heart beats, you're pumping oxygenated blood through ultimately through capillaries and things. But you're pumping through oxygenated blood, and that has a slightly different color than unoxygenated blood. And that PPG sensor is detecting that. So that's one sort of simple example of how you can use something like light and the details of how the light is coming back from things to measure some property. So right now, PPG sensors just measure the amount of oxygen in the blood, and they let you figure out how fast your heart is beating and so on. But one can imagine, people have hoped that it will be possible to make similar kinds of sensors that will detect other things in your blood. So for example, one that's very much been looked at, although still not successfully done, is detecting the amount of glucose in blood. That's relevant particularly for people who are diabetic, figuring out right now, the primary way to figure out how much glucose there is in your blood is to put a small catheter in and measure sort of the electrochemistry of the glucose inside you, so to speak. But if you could do that just with light, you would be able to do it non-invasively without sticking anything inside you. And potentially, there are probably hundreds, maybe thousands of different kinds of things that circulate around in our blood. And if you could have something that would be sort of a tricorder-like thing that would be able to sense just by shining the right kind of light and seeing what gets reflected back, would be able to sense all those things in your blood, you would have something that's a pretty decent approximation to the kind of Star Trek medical tricorder. And similarly, when it's like, what kind of rock is this? You can expect that to work as well. I think this is something that will actually be coming. I've been sort of waiting for it for a decade or so now, using hyperspectral imaging as a way to tell material, what a material actually is. But it's something I think is going to come. So let's see. Other questions here. When will we be able to 3D print medicines? That's an interesting question. So most medicines operate at a molecular scale. Most medicines, a very common thing that they're doing is there'll be some molecule that exists in you, and there'll be a molecule that normally does a particular thing. But if only you could jam, let's say it does something, and you want to stop it doing that thing. So it'll do the thing by basically, let's say, having other molecules come in and bind to a particular place on that molecule. They'll get stuck in a little sort of a hole in that molecule. It's a certain shape that's the right shape to fit the molecule that they're trying to fit in there. So one thing that some medicines do is they block those places where other molecules can bind. That's one example of what medicines can do. And so then what you want to do is you want to make a molecule of the right shape to stick it in that hole, so that you can have that medicine go and stick in the hole rather than having the molecule you don't want to go there. That's one example. Another example would be various kinds of medicines that attach to things on the surface of a cell, again, at a molecular scale. They're looking at this shape of molecule is kind of fitting like a lock and key into this other shape that's on the surface of the cell. So when you think about like 3D printing medicines, what you'd be trying to do there is to basically construct molecules that have exactly the right shape and also electrical charge distribution, but basically the right shape to fit into these places that you want to use medically. And so one of the questions, what sort of it's not discussed, maybe, I don't know, maybe it is discussed in science fiction, is the question of, can you make a machine that will essentially 3D print at a molecular scale? 3D printers we have today mostly work by having little tiny granules of plastic, for example, that they would fuse onto something that they're printing, something like that. or sometimes they have a sort of a thing where they use light, and they make they make it so that the thing will be hardened if the light fell there and not hardened if it isn't. Those kinds of things. But the question is, could you actually make a 3D printer that places individual atoms? So we have actually atomic force microscopes. That's a microscope for looking at things at an atomic scale, but you can also use that same technology to place individual atoms, but you can't do very many of them. It's not a thing where you could like build a big thing that way. But so one of the questions, which is kind of I think an important problem, is can you make a nanotechnology manufacturing machine that basically just you give it a specification, sort of a plan for make this molecule, and it will go off and somehow actually create that molecule. That's something in the next, I don't know, decade, 2, 3. It's something that I think might become possible. People kind of worked on that a lot about 20 years ago and sort of gave up. It's like, this is too hard. I'm never a great believer in the this is too hard theory. We don't know how to do it yet, but we could imagine something which is made from little molecules. Maybe, this molecule is controlled in this way and has a little head that tries to, put down carbon atoms in just the right place. I don't know. Some young person, because it may take a while, should start to try and figure out how to do this. Because if you can do this, you'll be able to make essentially a universal constructor of molecules of different shapes. I mean, when we do chemistry, for example, what we're doing is, we might have some way of doing chemical synthesis that you might learn in school or something, where it says heat this chemical, combine it with this, do that. It's a very indirect way of constructing molecules. We don't have a direct way of just saying, this is the shape of molecule I want, just assemble the atoms in the right way. But that's something that, and if we could do that, we could think about doing the equivalent of 3D printing medicines. We have another question here. How would teleportation work if we could make it happen? That's a kind of a complicated thing, because it's like, it actually relates to what I was just talking about constructing things at the level of atoms. Because let's say that what you could do is say, I've got a thing, and I will scan that thing at the atomic level. I would say, where's every atom in that thing? I've got my pen, and I say, I scan my pen, every atom in my pen. And then I simply send a signal to a printer that will then reassemble my pen atom for atom. Does that count as teleportation, or is that not fair because you had the original pen, and maybe you still have the original pen because the scanner didn't destroy it, but maybe the scanner had to destroy the pen, had to take it apart and then reassemble it at the other end. Does that count as teleportation or not? Do you have to sort of move things faster than the speed of light? That's a different issue. But anyway, so I think there are sort of questions about what that means. And also, if, for example, for an AI, for an artificial intelligence, if the artificial intelligence is, proudly figuring things out, and it's sitting inside my computer, and then somehow it's, and then I'm going to, can it be teleported to another computer? Well, the answer is yes. It's rather easy. You just take that, the program, the thing, what the AI is as a program, you just copy it to the other computer, and it's no big deal. It's just done teleportation. And as far as that AI is concerned, let's say the AI is connected to a webcam and it's watching me from my computer, and then, well, it's the bits of its program just get transferred to another computer, and they start up again, and there's another webcam on that computer, and it's looking at a different place. And it's like that AI just teleported itself, or got teleported. So it's kind of a thing. I think that's the more immediate version of teleportation that is likely to happen. The thing about taking a material object and having something sort of faster than a rocket, so to speak, to get from here to there, that's a more challenging thing that I think is possibly not something that we can expect to do in physics. Okay, next question was, why don't we have flying cars yet? I've seen, well, I've interacted with a few companies that say they're building flying cars. I think an interesting question. It's an interesting question. Why if you look back in the 1950s and you look at, Popular Science, Popular Mechanics magazine, they kept on having on the cover, flying cars. These are the cars of the future. Soon all our cars will be flying cars. Didn't happen. Why not? Well, the thing that got closest to flying cars was helicopters. Helicopters were sort of, they for many practical purposes, they're kind of like flying cars. And there was a period of time when, particularly, I think in the 1960s, 1970s, when it looked like helicopters are just going to make it. Everybody's going to have a personal helicopter. Why didn't that happen? I think one of the reasons it didn't happen is helicopters are very complicated, and they're hard to maintain. They have lots of things that sort of have to be very carefully maintained because you don't want your helicopter to just fall out of the sky one day. I don't know if that's really the reason, but my impression is that it's just much simpler to make a car than to make a helicopter. It's also the case that one of the issues is controlling a car is much easier than controlling a helicopter. I mean, a car, you're driving it along, you're pressing the gas, you're pressing the brake. If you stop doing those things, nothing terrible will happen for a few seconds. Helicopter, well, okay, so what are the things to understand? When airplanes were first being built, when the Wright brothers were first building their airplanes back in when was it? About 1900, a little bit after 1900. The challenge was, so it's pretty easy to make a kite. The problem is, how do you make a plane that can readily be controlled and so on? And so the big issue and the big innovation of the Wright brothers was figuring out not how to get the thing to get lift to go up, but how to control the thing so that you could make it fly in a definite controlled way and not become unstable and not just sort of keel over and fall into the ground. And that involved figuring out how to put little control surfaces on the wings that you could move and things like this. So that was kind of the big innovation, was how do you control it? For helicopters, the control problem is significantly more complicated. And I guess at the time when helicopters sort of looked like they might become popular, it was solving that control problem. The computers and things were not really up to being able to solve that control problem well. And you kind of needed a person, particularly when you're landing a helicopter. I once tried doing that. It's really hard because there are all these different physical effects going on, and you kind of have to, you have to wiggle things around in just the right way, or you don't successfully land the helicopter. Now, a thing that's happened more recently is quadcopters and other kind of multi-rotor, typically always electrical flying devices. And I think the reason that those have been able to happen, small drones, quadricopters, and so on are very common. The reason that was able to happen is because of the efficiency of electric motors and the efficiency of batteries. Because if your battery is so heavy that with the efficiency of electric motor you have to run the rotors and things, you just can't lift the thing off the ground. That doesn't work very well. And I think what's happened now is that we're just getting to the point where electrical batteries can store power efficiently enough, and the rotors can, the motors can operate efficiently enough that it's almost becoming possible to have kind of human-sized drones and so on that can, operate and can take off vertically and so on. So it could very well be that in the next few years there'll be something more like flying cars. It's a little unclear. There are a lot of details like, okay, you have a flying car and your flying car's motors stop working. Okay, there's one I've seen which has like 18 motors, and it's like they're all independent. They won't all stop working, or that's the theory at least. Or, there are other schemes like if the motors stop working, a parachute pops out. I mean, it's like elevators in buildings. There was a time when, I guess maybe 100 years ago or more, when elevators were a very unsafe thing. But then it got invented, the scheme got invented where if an elevator drops in a building, just as a purely mechanical thing, there'll be sort of brakes that shoot out from the side of the elevator and it will stop. And that's just a pure sort of mechanical engineering trick that made elevators much safer than they had been. And one can imagine similar things happening for flying cars. I don't think there are so. So I guess my answer would be it's probably to do with the control systems nowadays, to do with the way to get power, and whether you can get enough, whether you can store enough power, for example, electrically, to run electric motors that are powerful enough to lift something that is kind of human size. But my impression is, as I say, I've seen demos from several companies of things that are kind of flying car type form factors, typically which will take one or two people. So, it might be a coming thing. I have to say that the whole issue about how fast transportation would work and all those sorts of things keeps on changing, because like there was a time when supersonic planes were really like, that's going to be the thing that's really important. But the truth is, it's really important to have cars go much faster and so on. But then, then things happen, like cell phones get invented, and people are not they're not in a situation where, oh, you can't do anything when you're in the car, kind of thing. Or laptops got invented, and it's like you're sitting on a plane and you can't do anything. Well, actually, you can. You just get out your work and you're connected to the internet. And for somebody like me, it's kind of not that different from being at my desk. So some of these things that seem like, you really need this, but then it turns out, well, you don't quite need it as much as you thought, because something else changed in the technology. Okay, let's see. All kinds of questions here. Can I explain the physical difference between a 1 volt and a 2 volt battery? That's kind of interesting. Well, let's see. I mean, the batteries make use of electrochemistry. They make use of the fact that there are chemical processes that produce electricity. And essentially what you're doing when you make, it's kind of how much of those processes are you putting into the battery. Each one of those processes will kind of push the electrons that make electricity a certain amount. And if you put a bunch of them in series, you'll have more of those, you'll kind of push the electrons more. So actually, if you take apart some kinds of batteries, it's kind of a shocking thing, you'll find that, I don't know exactly, let me make one up, but like a 20-volt battery might actually consist of 5 separate pieces that are all 5-volt batteries, and they're all kind of lined up end to end, and together they make a 20-volt battery. So that's kind of at some level, that's the idea of what's going on. It's sort of as simple as that there's a certain amount of kind of push of electrons that happens from each of these kind of layers of chemicals, and you put more and more of those layers together, you'll push the electrons more with more voltage. Now how many electrons you push, that's a different issue. And so batteries are rated by the amount of power that they can produce, as well as the voltage. So that the amount of there's the question of how hard do you push the electrons, and there's a question of how many electrons do you push. The how hard do you push is the voltage. The how many electrons you push is the current. Voltage is measured in volts. Current is measured in amps or milliamps or whatever. And batteries will have, a particular battery will produce a certain amount of pushing of the electrons, a certain amount of number of electrons pushed, and that's sort of a rating of different kinds of batteries. Let's see. I have a question here from Manoj. Can we manipulate the weather and formation of clouds? And something about quantum mechanics, though. We're not sure that's relevant. So one of the questions is, can we control the weather? And I always find it interesting. Back in the earliest days of science, like 4,000 years ago, when the Babylonians were just starting to sort of talk about things scientifically, they would have their astrologers who would like predict things about what was going to happen in the world. And there were 3 kinds of things that they would often try to predict. They would try to predict, when will a planet rise in the sky? Will it rain tomorrow? And who will win this or that battle? Well, turns out the when will the planet rise, we really nailed that one. We can really do that very well now. Science has let us very well work out the motion of planets. Will it rain tomorrow? Science is still kind of a little bit on the edge of whether it can do that well. And who will win or lose a battle, that's a whole different story. But in terms of controlling the weather, okay, So there have been experiments done for about 50, 60 years trying to do what's called cloud seeding. Okay, so what is a cloud? A cloud is a big pile of steam, basically, a big pile of water vapor. And the way it works is because as you go up in the air, basically as you go further away from the Earth, the air gets thinner and thinner. And depending on how thin the air is, the water vapor, steam, may float on the air or not float on the air. Different kinds of things can happen. And so what happens in clouds, and I'm kind of cheating on some of the physics here, but basically what's happening is as the pressure of the air and the temperature of the air changes as you go up, a cloud, you'll either get steam or you won't get steam. You'll either get the water vapor turning into, you'll get a whole bunch of water vapor collecting, or you won't. And when water vapor collects, it makes a cloud. So then the question is, and that inside a cloud, it's like you just got steam, more or less. When you're going to get rain, what has to happen is that steam has to condense into little drops of water, and then and eventually those drops of water get heavy enough that they fall out of the cloud. So another thing that's happening is there are usually updrafts of air underneath the cloud that are kind of blowing things like water drops, potential raindrops up. Okay, so there's a big thing that happens in clouds. So how does rain get formed in clouds? So what has to happen is, first of all, these tiny, the steam has to start condensing, and you get larger and larger drops of, larger and larger little tiny pieces of water condensing out of the steam. And I think it's 18 microns, 18 micrometers, 18 millionths of a meter is, I think, a critical length at which that's the, when a cloud goes into an area of different temperature or different pressure, you can get little droplets of water up to about that size forming by essentially the steam condensing into water in these little drops. To get bigger than that, you need a different process, and you typically need water drops to run into each other, and you get a bunch of water drops running into each other, and after enough water drops have run into each other, they fall out of the cloud. And that's basically how rain gets made. So one question is, can you make those water drops form more quickly than they would normally in a cloud? So one of the tricky things is, okay, so let's say you've got a whole bunch of water vapor, and somewhere, and you cool the water vapor down, and it's going to turn into water, liquid water. Where is that changing into liquid water going to start? So turns out you can actually, it's the way the physics of it works out, you kind of have to have a seed of where the thing is going to start. If you just take the water vapor and you cool it down, all the atoms are running around in the water vapor, and none of them kind of start, there's no place where it starts kind of turning into a drop of liquid water. There's no place where it's called nucleates into a drop of water. It doesn't know where to do it. So you can often, you think that, water, steam condenses into water at 100 degrees centigrade. But actually, if you do it carefully enough, you can supercool steam so it's much colder than 100 degrees centigrade. And it's still steam, and it doesn't start forming little drops of water. But anytime there's any kind of, anytime there might be I don't know, a piece of dust or something in this water vapor, that will serve as a nucleation site, that will serve as a little seed, and that will start accumulating water, and you'll get this drop of water forming. So one of the things that it isn't actually known that well, how nucleation starts in water vapor and things like clouds, but what is believed to be the case is that if you could drop little dust-like things into the cloud, you might be able to start this process of forming drops of water more efficiently than would happen normally in the cloud, and then you would be able to make rain. So the thing that is most commonly done, sodium iodide is a common substance that people will take a plane and they'll splurt sodium iodide out of the plane into a cloud, and they'll see whether that causes cloud seeding, it's called, to happen, causes the water, the vapor in the cloud to form natural drops and fall down as rain. And so there are different places. I don't know. It was, I think, China Olympics was one place where I think this was attempted, where it's like, we don't want it to rain for the Olympics, so let's try and get the clouds to dump their water somewhere else. It's been very controversial whether cloud seeding really works, but that's our best effort to try and control the weather at that level is cloud seeding. That's the best known way to do that, and it's still a bit unknown whether that can work. I mean, there are other sorts of things that are more electromagnetic approaches to doing it, which so far don't really work. But that's kind of the state of that. Okay. Okay, so there's a comment from Jay here. Is there any merit to discussion about how about such questions, given that the actualization of our science fiction dreams is never literal? Human flight, planes, telepathy, teleportation, etc. You know, it's a question of how good your science fiction is, so to speak. You know, there are things that I think it's fair to say were sort of predicted in science fiction. Communication satellites is one that's often quoted. I haven't really gone back and looked at Arthur C. Clarke's writings about that. But and then there's the weird phenomenon that people know the science fiction so well that they use the ideas of science fiction to inform the way that they actually make technological devices. So a famous example of that was the early flip phones, early cell phones that flipped themselves open, just like a communicator in Star Trek. Actually, I never could get my flip phone. I couldn't actually, like, you know, throw it in the way that a Star Trek communicator can be opened, but it was close enough. You opened it yourself, and that was a case of where sort of fact was following fiction because people kind of knew that fiction. It was a kind of a familiar approach to things. I would say that you know, one has a certain amount of fun kind of imitating things which are known memes, known ideas that come from science fiction, like the HAL computer of 2001 has been endlessly sort of imitated and riffed on because it's sort of a familiar picture of what technology might be like. This question of can one accurately predict what will happen? Do things work the way one expects them to work? Well, it's a question of how well one predicts them. I mean, I think in my life, some of the things that I've you know, I've been very much into trying to figure out what's going to happen. And sometimes you can see certain kinds of things that are sort of inexorably going to happen. You can't necessarily tell how long it will take. And some details may be different, but there are things which are kind of inexorably going to happen, and there are things that are big surprises. And I think, oh, I don't know, one that my wife is fond of reminding me of. This was back in the, when was it? It must have been the early 1990s. We're building a house, and there was a question of, you know, we're going to have some place where we want to put a television. And there's a question of, because of something about the construction, it was the most convenient thing was just to have this very, not very deep, like a few inch deep kind of area. I never watch television, so I don't really care where the television goes. But anyway, this was you know, put a television somewhere, and you know, I said, and it's like, is it going to be enough to have, you know, a 4-inch deep kind of recessed thing to put a television there? And you know, at the time, televisions were made with cathode ray tubes, and they were these big things that were, you know, if they were a large television, it would be a deep thing, several feet deep, and so on. And I was like, no, definitely there will be flat screen televisions. Okay. And so, you know, built this house with this setup. And well, turns out there weren't flat screen televisions at the time when the house was built. Actually, flat screen televisions came in about 10 or 15 years later. What was the mistake? The mistake was very subtle, because I knew perfectly well that the technology existed. LCD, liquid crystal display technology existed. In fact, I'd even seen in technology labs, I'd even seen demo versions of LCD displays, but they did not become commercially common for a decade or more after that time. What went wrong with that prediction? What went wrong was something I absolutely didn't expect. See, the fact is when you make an LCD display, it has lots of little pixels in it. That's how the display is made. And normally when you manufacture something like that, you might have 10 million pixels. And it might be that 20 of those pixels don't work correctly. Now, for some purposes, it's not going to matter that 20 of those pixels don't work. But if you're seeing a display and 20 pixels on that display never change, they're always black, well, gosh, you'd notice that immediately. And so what went wrong was that while it was possible to make one of these displays, there was some probability, some rate at which the pixels would be bad. And the chance that you would get no bad pixels in a 10 million pixel display was very low. So you could make these displays, but if you wanted to make sure that they were all perfect, you'd have to make millions of displays to pick off the one that was good enough to actually sell. And it took a long time to get to the point where it was possible to manufacture them so that there would be few enough errors that most of the flat screen televisions you made would actually work. So it is a very interesting problem. I mean, it's a great exercise to try to figure out, given a thing, given something which is technically possible or scientifically possible, how will it be used? So, for example, one right now is space and the availability of low-cost satellites in Earth orbit. How will they be used? What will we be able to do? Like, for example, things that are coming are real-time daily imagery of the Earth. So being able to get, I'm actually a little bit surprised. There are a couple of companies that were doing that, and I actually haven't heard from them for a while, so I don't quite know what's happened with them. But we're going to be making available imagery of every place on the Earth to like 1 meter resolution every once a day. And actually kind of so that you can make comparisons between what the Earth looks like on one day, what some particular place looks like on one day, and the next day, there'd be a particular local time, like who knows what it is, 10:30 a.m. or something, where the satellites come over and they're going to take a picture. Because that way you're comparing, the shadows will be more or less the same between two successive days if it's always at the same local time each day. And obviously, sometimes, if it's cloudy that day, you won't be able to see to the surface, at least not with visible light. Otherwise it's like, okay, the satellite's coming over. Let's go wave a flag at the satellite because we know it's going to come over at exactly 10:30 a.m. or something. But in any case, that's the thing. So real-time imagery of or not real-time, but at least daily imagery of the Earth's surface. Later on, maybe real-time imagery of the Earth's surface is one thing that's coming. We don't really know what that'll be used for. It's already useful, for example, for understanding crops, for example. That's a place where people use that. There are kind of in the world of trying to do financial kinds of things. People are trying to predict how well is the store doing. Let's see how many people are in its parking lot today. Let's count the number of cars in the parking lot. Right now, that'll be in most places very, very small. But let's count the number of cars in the parking lot, maybe as a way to figure out how well the store is doing. And let's do that by having a satellite image of that parking lot. So there are use cases like that. But there are other things that people wonder about. Like, for example, a big possibility is cell phone, being able to provide cell phone service from orbit. That's not quite as easy as it sounds, because when you have a little cell phone, it's easy enough to have a satellite that's powerful enough, that has a radio antenna powerful enough to reach your cell phone. It's much harder for your cell phone with its little battery and with you holding it up to your head and so on to emit radio waves that are powerful enough to be detected by the satellite. So it's useful if you're making kind of base stations of places where you're communicating with lots of cell phones. It's a little less useful if you want an individual cell phone to communicate with the satellite. But it's an interesting question. What will be, if it's really cheap to put things in orbit, what will we do with them? And, people sort of say, well, we'll have ads in orbit and so on, and we'll have, people said for a while, it'll be a good place to grow crystals because it's easier to grow crystals in the microgravity, in essentially weightless state that things are when they're orbiting in orbit and things. But it's not clear what it's a good exercise to try and figure out. And I like doing these things because, I kind of try to try to figure out what's going to happen, and then I sort of maybe even write it down, or at least remember it. And then 5 years goes by, 10 years goes by, and it's like, okay, I knew that was going to happen, or whoops, I didn't see that coming. Let me use that mistake to inform later things that I try to predict. Okay. Okay, I'm going to take, let's see, a number of very interesting questions here. All right. Hard to choose between them. All right. There's a question here from Jamie asking, what are my thoughts on Starshot projects that will attempt shooting satellites to Alpha Centauri with lasers? So, the traditional view of how do you send a spacecraft somewhere is you have your spacecraft, you have a rocket, it has rocket fuel, you burn the rocket fuel, and it produces it sends gas at high speed out of the back of the rocket, and that's what pushes the rocket forward. But typically, that happens only for a short time, and then you've burnt up all the fuel, and then the rocket just coasts after that. Well, if you want to get to Alpha Centauri, which is 4 light years away, it's let's see how many million miles away. I'd have to do some math or ask Wolfram for that. But it's millions of miles away, and to reach it, going if you just the fastest rockets that we've made go at about 100,000 miles an hour. And reaching Alpha Centauri at that speed would take a ridiculously long time. And the question is, can you make a rocket that will just keep accelerating, keep going faster and faster and faster and faster until it gets up to something even close to the speed of light, and get it to make it all the way to Alpha Centauri? So one scheme for doing that is, instead of having the rocket have fuel on the rocket, you have something where you're essentially pushing the rocket from Earth and just having it, keeping on pushing it. And so I think I mentioned in one of these other live streams, the idea of radiation pressure and solar sailing. When light hits a mirror, it pushes the mirror just a little tiny bit, because the photon of light, just like you'd hit something with like a billiard ball, and the billiard ball will bounce off. When the billiard ball bounces off, it pushes the thing that it bounces from. Well, similarly, when a photon of light hits a mirror, when it bounces off, it's pushing the mirror just a little bit. And so the idea is to have a laser on the Earth, high power laser, that will just keep pushing this sort of solar sail. That would be a big, big piece of very light material that is in space and reflects the light back, and keep pushing that and keep pushing it and keep pushing it, and use that to make the thing go really fast. Now, eventually, it gets so far away that the laser from the Earth spreads out too much. There's not enough. You don't get enough intensity of laser light on the sail, and it can't really push it any further. But that's kind of the idea. And actually, I have one of these little things. I got them from somebody. The little tiny prototypes of those starships, so to speak. They're about that big, and they have little antennae that hang out. They're little tiny pieces of wire that hang out that might be able to produce a very, very not very intense radio signal, maybe intense enough that we could detect it with a really big radio telescope. But so I think it's an interesting idea. I think it's pretty challenging. I think that it's kind of our most obvious short-term hope for getting something that will be a spacecraft that can go to Alpha Centauri. And kind of the idea is you send off a whole swarm of these little tiny spacecraft, and you hope that some of them will make it to Alpha Centauri, will be able to, maybe we'll be able to get some data from there, and that you'd be able to pick up radio signals from them and learn about what's going on there. Now, another thing that happens is telescopes are limited in just the properties of light. limit how far away a telescope can resolve things. So, for example, you might say, let's have a telescope that's, on the Earth, and it's just looking at Alpha Centauri, and let's just make our telescope really big and really high magnification, and let's just see if there's anybody hanging out on planets around Alpha Centauri or something. Well, the reason that doesn't work is because there's a limit on how good a telescope we can make, and that limit is a result of properties of light. Basically, in order to make a really, really good telescope, you have to be able to focus light really, really well. And because light acts like a wave that's of a certain size, you can't focus the light down into a size that's kind of small compared to the size of the wave that corresponds to the light. That's one problem. The other problem is the Earth's atmosphere kind of fuzzes things out. So let's say you put a telescope in orbit, like the Hubble Space Telescope. Then you're not dealing with the Earth's atmosphere. Maybe you put it on the far side of the moon. You don't have all the light from the Earth and so on. You've got your telescope there. And now you want to make a telescope that has a really high resolution, that can really see things. So it helps to have a really big telescope, to have a really big aperture for your telescope. There's a formula that tells you how well the telescope will be able to see, how much it can resolve based on basically the size of the telescope. But even then, there are some limits. But one of the things that we're sort of learning slowly is that by playing some tricks with quantum mechanics and looking at light as particles, photons, and looking at not just one photon, but multiple photons all together, it may be possible to make sort of much, much better telescopes that kind of that sort of get around the limitations that we thought existed in how good a telescope you can make. So it may actually be possible to, quote, directly see things that are at very high resolution, that are from, just the very small amount of light that's making it to us from, let's say, a planet around Alpha Centauri. We might be able to actually pick that up and reconstruct from those few photons of light that are arriving. We might be able to reconstruct even images of things there. And that may be a better way to kind of find out what's going on there than send a little spacecraft. I don't know. We have to see. Okay, let's see. There's a question here from Einstein von Rembrandt. Could a technologically advanced civilization arise on a planet completely covered in water? Oh, of course. I mean, the idea that, that civilization has to be exactly the way that our civilization is just because that's the one example of civilization we know. I mean, could whales have constructed a civilization if left for enough millions of years? I don't see why not. I mean, the details of, it's like things you can make with flippers rather than things you can make with hands. Well, they're different things you can make. Who knows? Maybe the whales are even making them and we just don't recognize them. Maybe they're making amazing sort of whale artifacts by arranging, by flipping their flippers around to arrange the pattern of plankton in the ocean to be a particular way. Well, we don't even notice because we don't have detectors and we don't recognize what they're doing. I mean, it's kind of like recognizing archaeological artifacts on the Earth of, is this a stone circle or do these stones just happen to be this way? So, I think that it's something where, yeah, I think, the particular way that our civilization has developed is just a lot of accidents of history. And I just don't think that there's anything that would prevent that. I mean, I think that's of interest because there are certainly outer planets. I'm trying to remember, what is it? Enceladus, moon of Saturn. I'm not remembering my astronomy very well. And I guess recently Pluto, it's claimed, probably has a liquid water or liquid ocean inside it. I mean, it's kind of bizarre that Pluto, very, very far away from the sun, can still maintain potentially liquid water inside it. How does that happen? Well, it happens because when Pluto was originally formed, it was hot. And you might say, well, gosh, that was 4 billion years ago. How come it's still hot inside? Well, it turns out that through rock, heat doesn't transport very efficiently. And you could actually have something which is like you have you might use styrofoam or something to try and keep heat in, or you have a thermos flask or something like this to try and sort of keep heat into something. And you might And that works up to a point. But by the time you have a big layer of rock, it turns out you can keep stuff hot for a really long time, like billions of years. Actually, two things going on. So the heat of the Earth. So if you drill down in the Earth, as you probably know, the Earth has a liquid core. So there's rock on the surface of the Earth. That's the crust of the Earth. If you drill down like 50 miles or something, you'll get to the liquid core of the Earth. People haven't been able to drill anything like that far. They've drilled to the point where it's getting pretty hot, but not to the point where you're actually at the liquid where it starts to be liquid. But so the Earth is liquid inside. It's hot inside. At the very center of the Earth is thousands of degrees centigrade. How does it come to be hot inside? Well, there are two reasons it's thought. One is, well, it didn't cool down from when it was formed 4.6 billion years ago. It's still cooling down inside as heat is gradually transmitted to the surface and then radiated into space. That's thing number one. Thing number two, there are radioactive elements in the Earth, like uranium, that slowly decay, and slowly their nuclei fall apart. And when their nuclei fall apart, they produce heat. And some of those elements, because of the way the nuclear physics works in those elements, take billions of years to decay. And so they're still decaying now. The elements that were put into the Earth when it was first formed are still decaying now. And so some part of the heat of the Earth comes from radioactive decay. Some part of it is remnant heat from when the Earth was formed. Same presumably happens in things like Pluto. And that's why, even though you're far, far away from the sun, you can have liquid water. Now, there are people think about, I think Enceladus, there's discussions about spacecraft missions there, where it's like, can you drill through 2 kilometers of ice or something on the surface to get to the ocean underneath? And what kind of weird spacecraft do you need to be able to do that? And if you drill through, it's kind of been, it's been sterile for 1 billion years or something under there. There's nothing from the outside probably has managed to get in. So like there could be all kinds of critters in there. And it'd be kind of embarrassing and upsetting if we drilled through their ice and suddenly we get to the inside and we kill them all off. That would be really bad. So it's a but I think this idea is kind of an interesting thing to imagine. If you're a critter that lives inside this liquid core inside Pluto, let's say, and there's nothing outside. You don't know what's outside, and people would have all these theories about how we're inside this liquid core of this planet or something. There'd probably be some crazy scientist who'd be saying, well, actually, if we just were able to drill through the sky, so to speak, we'd get to something different on the other side, and everybody would think that person that critter was nuts. So, okay, questions here. I should wrap up soon, but let me look at a few of these. Oh, there's a question here from Luis. Can a tardigrade survive on Mars? So tardigrades are these, what are they called? They're also called what are they called? They're these kind of very ugly looking creatures. They're very small, and they can basically hibernate for a really long time. And and they can survive when it's really cold, when it's really, they don't have to eat anything. They're just sort of frozen for long periods of time. And I think the answer is, okay, so a friend of mine who has a project called the ARC mission, whose goal is to put human artifacts around the solar system, put a little package of stuff onto an Israeli spacecraft, this was last year, that went to the moon. And the idea was the spacecraft would do a soft landing on the moon, and these artifacts from the Earth that included all kinds of micro versions of all sorts of books and things would sit on the moon for the next however many years, and sort of safely backed up relative to the Earth. Okay, that was the idea. Unfortunately, due to a malfunction on the spacecraft crashed into the lunar surface at 2,000 kilometers an hour. So this payload, we initially thought the payload would have just been vaporized, but actually what happened was the spacecraft crashed into the moon at a very glancing angle. And almost certainly, based on photographs from the Lunar Reconnaissance Orbiter, almost certainly the spacecraft hit the lunar surface and actually bounced and probably slid maybe as much as a kilometer, because there isn't as much gravity. There's only 1/6 the gravity on the moon. And also, so long as you don't hit a boulder, you can just slide on the surface of the moon a really pretty long way. So most likely the spacecraft was actually not completely destroyed, and this payload probably survived and is probably on the moon somewhere. Okay, in a piece of, I would say, not very good judgment, one of the things this friend of mine put in the payload was a bunch of tardigrades. And so these critters, who were supposed to be in a very sealed container, but a container that's sealed, if you crash it into the moon at 2,000 kilometers an hour, what you thought was sealed might not be so sealed anymore. But so there are some tardigrades on the moon, and I think the expectation is that they survive, and that if they were rehydrated, if they were put in water again and things at a reasonable temperature, that they would just come back and sort of be happy tappers again, I think. Okay, so let's see. There's a comment here. We should build a pyramid on the moon. That'd be cool. It's a kind of artifact. You know, the pyramids are one of the human artifacts that has lasted the longest. You know, it's a big question. What do you put on the moon? Okay, so I have another friend who has a project to search for artifacts on the moon. And so his idea is take all the lunar reconnaissance photography and search for things that might be artifacts. Like, what if some civilization had visited the moon and put a pyramid there? Would we even know it? Well, we have pretty high resolution photography of the surface of the moon now. But so we might go through and we look at the surface of the moon and we say, is there anything that looks like it was made by somebody on purpose or something on purpose? Well, if we saw a pyramid, it's like, what would we conclude? Okay, so, and yes, in the movie 2001, came out in 1968, one of the dramatic things in that movie was the thing called TMA-1, which stood in the movie for Tycho Magnetic Anomaly. Tycho is a crater on the moon, and the idea was that the storyline was that it had been detected that there was this intense source of magnetism in that crater, and then it was excavated, and then what was there was this slab that was a black slab with its length ratio is 1:4:9, and the black slab just sat there, except when the black slab was exposed to the sun, it sent out an intense radio signal. Okay, so that was the concept of the movie was, if you saw this perfect black slab, you would immediately know that was the thing that was created on purpose. And there was a philosopher actually from a couple of centuries ago, Immanuel Kant, who said, you know, if we saw a hexagon drawn in the sand, we would know that must have been created on purpose. Nothing would naturally have done that. It's too perfect. It's too mathematical, so to speak, to have been created any other way. Well, you might say that, but it turns out that there are actually things that happen because of wind and sort of swirling patterns of wind that actually make hexagons in sand. So it's kind of like, well, we see a hexagon in the sand. Can we really conclude somebody drew it on purpose? Not really. The wind could have made it. And the really embarrassing thing about hexagons is if you look at the North Pole of Saturn and you look at it in spacecraft photographs, it has a giant hexagon that is the shape of a storm near the North Pole of Saturn. So we don't think anybody did that on purpose. Anything did that on purpose. It's just the way that the physics of the atmosphere of Saturn works that it makes this hexagon. And so the thing that so this idea of what do you put on the moon that makes it look like makes it look like kind of something intelligent did it. it's not very obvious. And it's not even obvious on the Earth. You know, you look at the Earth. I asked years ago, I asked some astronauts I knew, you know, what do you see on the Earth that makes it obvious that there's a civilization here? Said, what do you see? And, you know, what features of the Earth make civilization obvious? So at the time, they said the most obvious thing is in the Great Salt Lake in Utah, there is a perfect straight line that separates one part of the lake that is one color and another part of the lake that's another color. And it's a kind of a straight line that you see from orbit. And it turns out that's a causeway that was built, and that there's algae of one kind on one side and there's algae of another kind on the other side. So they tend to be different colors. So it's a sort of dramatic line. I said, what else do you see? Okay, so there's another thing in New Zealand. There's Mount Egmont, I think it is I think it has a new name actually. That's an indigenous name, which I now forget. But there's a Mount Egmont, and I was doing this research for this book I wrote in the 1990s, and was sort of before the web was popular, so I had to like send email to people and ask questions and things. There's this volcano in New Zealand, and there's a sort of perfect circle around this volcano. And so I wanted to get information about this. So we contacted the New Zealand Geological Survey, and they said, you know, if you're writing a geology textbook, please don't say that the crater of this volcano is a perfect circle. The perfect circle there has nothing to do with the volcano. It has to do with the fact that there's a boundary of a national park that was drawn as a perfect circle, and there are sheep that graze, I forget whether it's outside or inside the national park. And so the grass is different on the two sides of the inside the circle as opposed to outside the circle, and that's what makes the perfect circular pattern. But that's another piece of evidence of sort of human civilization on the Earth. But it's actually pretty hard to find these things. And you know, the fact that if you look at other places on the Earth, there are actually pretty good circular, pretty close to circular craters and pretty close to circular other features on the Earth. And it's really hard to tell, you know, was that an intentionally drawn national park, or was it just a natural phenomenon? So this project to go see whether there are artifacts on the moon, it's an interesting but challenging project, because, like, you know, it could be that was a great alien artist who drew this amazing picture on the surface of the moon that is a fantastic piece of alien art, but we just wouldn't recognize it because it doesn't have anything that relates to kind of our notions of what represents order. Okay, I'm noticing Pingu asking, I'm sure Elon Musk will do worse things to the moon than polluting it with water bears. Okay, I don't know whether I should tell this story, but I don't tend to tell too many of these. But I just, there's a conversation I had with Elon a few years ago that just featured a priceless line, I thought. I was mentioning the so-called terraforming of Mars. We were talking about kind of how, whether it's realistic to get the atmosphere of Mars to be I have to tell you a little bit of backstory here, but whether it's possible to get Mars to have an atmosphere more like the Earth. And I mentioned earlier this idea of detonating a bunch of hydrogen bombs near the poles of Mars that have ice in them, and causing and producing, you know, putting water vapor into the Martian atmosphere that way. So anyway, okay, so that's first thing. Second thing, I have to tell you a little bit of historical story. So when people were doing archaeology, particularly in the 1800s, it became very popular to try and excavate ancient sites. And the thing that so there was these things that have been described in, for example, Homer had described the city of Troy. You know, the Iliad is all about the Trojan Wars and you know, all the stuff that was going on around the city of Troy. But nobody had found the city of Troy. It wasn't clear whether that was just a story that Homer had made up, or whether there was actually a city of Troy. So there was a German archaeologist named Schliemann who went to find the city of Troy. And he eventually did find the city of Troy. But it turns out that, like many ancient cities, Troy was built in many layers. So there was, you know, Troy 1, Troy 2, Troy 3, and, you know, after 100 years or something, Troy would be, I don't know what would happen to it. Maybe the Greeks would invade, like in the Trojan War, and they would and all the buildings would collapse or something, and then they build another version of Troy on top of it. So there were many layers of Troy. So one of the things that that Schliemann did was trying to get through all these layers of Troy. He was like, the first layer, well, it's not very interesting. The one at the top, not very interesting. Let's just use dynamite to blow through the top layers. And because we really want to get down to the layer that Homer talked about far below. So he used dynamite and blew up the top few layers of Troy. In fact, he probably blew through the first the layer of Troy that might have been the one that Homer was describing. Okay, so that's a bit of backstory. But anyway, this conversation fragment that I just thought was kind of funny was Elon was explaining to me about how, this whole idea of detonating hydrogen bombs on Mars, and we've been talking about, life on Mars and so on. And so my comment was, well, then, it was about life on Mars and so on. It's like, if you do that, if you detonate hydrogen bombs on the poles of Mars, you'll be the Schliemann of Mars, because it's like, just like if there was ever any life on Mars, on the poles of Mars, you just blew it up with hydrogen bombs. So anyway, I just thought that was a funny, as conversation fragments go, kind of out of context, it's kind of a weird thing to explain. But I think it's not. I think that's amusing enough to be repeated, so to speak. Okay, I'm just maybe one more, and then we should wrap up for today. Let's see. Oh, there's two good ones here. Why haven't prehistoric animals been resurrected yet? Okay, I'm going to talk about prehistoric animals, and I'm going to talk about antimatter for a second. Okay, the question was, why haven't prehistoric animals been resurrected yet? So, first question is, so we know the DNA, the genetic material of current organisms, and we can actually figure out from knowing about different organisms, birds, reptiles, mammals, etc. We can extrapolate back to some extent what the ancestors of those animals must have been like, what kind of DNA they might have had. And we know a certain amount from that. It'd be really convenient if we could actually get the actual DNA of, for example, an actual dinosaur. And the movie Jurassic Park, for example, features sort of DNA extracted from a dinosaur DNA that's then going to be recreated. Actually, a friend of mine was the science consultant for that movie, and one of the things he regrets about the movie was, at the time of the movie, he's a paleontologist and studies fossils and things, and he had a bunch of theories, and he put basically all his theories into that movie, and it turns out about half the theories were right and half the theories were wrong. But he says everybody now believes all of the theories, including the ones that were completely wrong, because they're in that movie. And so it's kind of so there are things in that movie that are just, turned out they just don't work. They're just not right. There are other ones that are right. But so it's kind of funny that's how science fiction becomes science, so to speak, or maybe even gets science a bit off track in that case. I think the main result is to be able to anyway. So the concept in that movie was dragonfly, not dragonfly, mosquito, sucks blood of dinosaur, which has DNA in it. Mosquito gets trapped in a piece of amber, lasts for 100 million years. We get the mosquito, the DNA molecules are very stable. So there's a decent chance we could extract the DNA from that and figure out the DNA of the dinosaur. That hasn't happened yet. We do have, somebody's pointing out on the live stream here, we do have mammoth DNA. That's because we actually have mammoths. Mammoths existed up until Roman times. There were still mammoths. Mammoths, there are mammoths that have been found frozen in Siberian permafrost and so on. So, mammoths are out, well, they're not out and about, but they are, you can find a fully existent mammoth, so to speak, and extract its DNA. Now, can we make a can we use that DNA to make a viable baby mammoth? I suspect the answer is yes. I mean, I suspect, I've forgotten what's happened to this. I mean, a few years ago, people were very enthusiastic about growing mammoths and in elephants and so on. I don't know what's happened to that. But I would fully expect that that will be something that's possible. Whether you'll be able to get a pet stegosaurus running around from 100 million years ago, that's less clear. But I kind of think that that will eventually be possible. It requires possibly, you won't have the DNA. You'll have to manufacture the DNA, and it's difficult to manufacture a whole long DNA sequence like that. But it's becoming progressively easier. Then you have to find, when you create an organism, there's more to the organism than just its DNA. You have to have sort of something which will at least pretend to be something like the egg, so to speak, the other things in the dinosaur egg that aren't just the DNA that codes for the construction of the dinosaur. So that will be a challenge. But I would fully expect that in time it will be possible to do that, and it'll be kind of interesting. And it's there's sort of a trade-off between reconstructing ancient animals and making a designer critter for yourself. I mean, it's another thing that's in science fiction, famously in a movie called Blade Runner. Starts with this genetic tinkerer, so to speak, who's created all these creatures that were capable of doing things like instead of having technology, electrical technology that opens your door and things, it's like have a little creature that's sole function is opening the door for you and so on. And that was actually, I would say that about 30 years ago, a person who wasn't one of my favorites actually, but who died recently, but he was a very contrarian kind of fellow. And he kept on saying, computers aren't the thing. All this electronics, that's not the future of technology. The future of technology is custom biology. In other words, the future of technology is not to make a digital device with electricity and so on. The future of technology is to engineer a creature that will do what you want. So instead of making, I don't know what, instead of making your flying car, make a creature that has these wings that people can just sit on the back of this creature and it will take off and take them places. That will be a better way to build technology than to use electronics and so on. Turns out so far that profoundly did not work. And although when we want to connect to sort of biomedical things, we are interested in making molecular scale things that sort of fit into our biology. But when it comes to your typical technological thing, the electrical digital thing is much better. All right, I think we should wrap it up for here. Someone's saying they don't want a mammoth pet. They want a clone that can work 2 shifts. They want to make a clone of themselves. One of the things that I'm curious about is I record a lot of stuff that I do. So, when I type, I record every keystroke. I record all the emails. I've been doing that for like 30 years. And so I've collected millions of emails, huge amounts of stuff that I've produced. I'm recording this live stream and so on. So the question is, at what point will there be enough data about me that you could basically reconstruct me? At what point will there be something where you've seen enough millions of, I got this email, I responded this way, that you could make essentially an AI that will respond in the same way? That's a fun question. And there's a separate issue, which is a biological clone. And maybe another time we'll talk about cloning humans and that whole story. It's an interesting, I'll say one thing about that. As people may know, in the 1990s, there was, normally, we all have certain DNA. And the only way that we get to sort of make use of that DNA, if we're mammals or something, is to have children, and the children make use of half of our DNA. But the other idea is you just take the DNA and you make an identical copy of the organism by just saying, I'll just grow an organism with that particular DNA. So that was something that people had said for years, mammalian cloning is impossible. They just said, just can't work, just can't be done. And I used to ask people, why is it impossible? Why, explain to me, why is it impossible? Why can't we take the DNA out of one egg cell and put it in another and restart the thing and have it all work and so on. And we give explanations. It's like, why isn't it possible? Well, it turned out in the mid-1990s, people discovered how to do that in fact, for a sheep, first of all. And it's a weird process. It involves electricity and it involves a bunch of other things. But in the end, that procedure lets one make a clone, in that case, of a sheep. So, mammalian cloning is possible. Is it, in the case of, there's a lot to say about cloning of humans, human organs, things like that. Maybe we'll talk about that another time. All right. Oh boy, there's a comment from Luis here. It'd be interesting to engineer a seed to grow a house. Yeah, that's a cool idea. I mean, people have looked at that. I mean, the notion of, can you want to grow a tree house? Can you make a tree that will grow in the shape of a house, so to speak? Can you make something where you have sort of a growing house? Forget the idea that your house, it's kind of like the ultimate, I don't know what, a thing where you make your house not out of wood that way of trees that you cut down, but of trees that are actually growing, and somehow you control, you can actually control the growth of trees. Plants have these things called auxins, which are like our hormones, and those determine the growth of plants. So for example, if you want to make a tree sprout a branch, to some extent you can do that by just sort of injecting this plant auxin, and that will make it kind of grow a branch in a certain way. So you might ask the question, could you make this tree so that it will grow in just the right shape to make the house your dream house, so to speak? And I don't think we know you can't do that. So it's kind of maybe a coming attraction of the ultimate eco house is a house that is made out of growing trees. All right, I think we've veered off into some curious things, but let's wrap it up here, and I think I should be able to continue with this next week if people are interested. So thanks for joining us, and thanks for a lot of fun questions. You've made me think about a lot of things that I don't normally think about, so I appreciate that. Thanks very much. Bye.